Good afternoon, this is Schweitzer, and this is a little preliminary video that's going to cover not only a little bit about how our lab is going to run, but also some background information on the actual lab or lab concept or lab topic. So, overall objective here is to determine the molar mass of an unknown gas and to possibly identify the gas via gas collection. So a couple of things first here is that we have a list of possible unknown gases. We have methane, which is simply just one carbon, ethane, two carbons, and those are hydrogens. We have propane, and we have butane. Another one might be what's called isobutane, which you may have heard of. They do use this in a lot of camping grills. You can buy isobutane at the local Gander Mountain or whatever. Looks like this. C4H10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is also, of course, C4H10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's go with pentane, which is C5H12, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, so our overall objective is to try and figure out the molar mass of this thing, and then we'll match up the molar mass with other substances. For example, the molar mass of butane is 12, 13, 14, 15, it is 16 grams per mole. And which of these molar masses matches up with our unknown molar mass? So let's look at our calculation for molar mass. Our molar mass is equals to the grams of a substance per mole of a substance. So we have two calculations. And through the procedure, you'll see where we're going to get these pieces of information. Alright, let's take a moment and walk through our procedure. First things first is we're using a lighter, a typical stick lighter is what we'd be using. And if you know the gas, or you think you know what's in a lighter, well, then you can use this experiment to sort of verify what you know. You obviously could possibly even Google what is in a butane or isobutane, or is it methane, or what is in a lighter. So either way, we have ourselves a lighter, and what I did was I took a stick lighter like this, and the tank is inside here, and there's a little long tube that runs up to the tip. And I removed all the outside pieces, and now you'll find that we just have this reservoir with a removable little tube. It's probably about 4 inches long, 5 inches long. So the first thing we're going to do is we're going to set up our gas collection. Now we're calling this gas collection. So we're sort of trapping the gas collection over water. That means we're going to take a pool of water. In this case, I usually use a 5-gallon bucket, but you really don't need to use that either. It's going to be filled the majority of the way full of water, and we're going to have what's called a eudiometer tube or a gas collection tube, and you're simply going to fill this thing all the way up with water. So this will be completely full of just tap water. Then you'll place your thumb over the top of this thing, and just so that no that's unusual. All right, so that no water can get out, no air can get in. Invert it, and you'll find that this thing will, once inside the tube upside down, that no matter how you place it in here, as long as the opening doesn't exit the water, all the water stays up in the tube. It doesn't slump down. You shouldn't have zero bubbles or anything of that nature in the top here. So a little bit about the physics of what's going on here. In physics, we have these things that are called forces. And in any item or any object, if you take an object, let's say, and you put it on a frictionless surface, okay, so absolutely no friction, just for this example, and you come across here and you push or apply a force. Let's make this guy into just a force. You apply a force in this direction. Then the object will accelerate in that direction. It makes sense. You give it a push and it moves. But if I were to take another object and apply the same force to it in that direction and it doesn't move, that means there must be some opposing force on this thing, and they must be equal and opposite. Many times this force applied is equaling what we call the force of friction, and at that point there is no net movement. There's no net force, and therefore there's no net acceleration. This is occurring inside this tube. Now you'll notice that in the tube here we have this water above the tube. That is caused by a downward force due to gravity. I mean, if I took this tube out of the water and just simply held it over the air like this, it would, and if the water didn't just flow right out, you would be probably dumbfounded and shocked, right? So why is it that the water doesn't fall out when it's inside the tube of water? And the reason for that is because there must be some opposing force. And at this point, it looks to me like it's enough to keep the water up. You might think of it even a mental experiment or a thought experiment to say, okay, if I have myself a bucket, how tall of a tube would it take, potentially, for you to fill it, invert it, and for it to stay full? I mean, would it be infinite? I don't think so. I mean, at some point, your force of gravity has to be big enough that this opposing force, whatever it might be, we haven't really said yet, wouldn't be able to match it. That opposing force happens to be the force of the atmosphere. The atmosphere pushes down, and therefore pressures up, and it pushes up. And that counterbalances the force of gravity. And there is a point, and it's about, surprisingly, 32 feet high before you would start to have this tube continue, and it would just slouch down to that point of 32 feet. That is essentially the weight of all the atmosphere pushing down on this thing, pushing back up. And every little kid who's going through, through McDonald's can stick their finger over a straw and hold the water there and create that little bit of an atmospheric push. All right, so now what's happening? What are we going to do here? Well, we're going to take this tube, okay, that is full of water, okay, and we're going to take our lighter. Okay, now before we use that, we're going to take our lighter, take the little tube off, so the tube is missing, and we will mass the original weight of the lighter. Then we put the tube back on. Okay, the tube just slides on. Then, usually with a partner, because you don't want this thing to get wet. The masses of this lighter we're using are so small, you want to keep that lighter dry. So bring the lighter pretty close. Okay, and again, you can maneuver this tube pretty easily. Just don't take it out. It's full of liquid. Run your tube under it and start releasing gas so that you end up having the level of the gas inside it. So we're going to start creating a pocket of gas inside here. make it so that the pocket of gas matches the area, the level of the water. And of course, you might notice, even pull out your lighter, and if you move this tube up and down, you will notice that volume of water changes. Because in the case, if we have this tube looking like this, okay, so let's get just a little side note here. If we have our tube and we have this upside down here, and we have, okay, the force of gravity here is pulling this water up, and then the line, let's say, is right here. Well, then I have two forces. I have the force of the pressure of the atmosphere on one side. I have the force of gravity pulling that liquid right here down, and I have this gas inside here that's also pushing in the only place it can, which is down, pressure of the gas. So I have a bit of a teeter-totter. On one side I have the pressure of my gas, and on the other, and I have the pressure of gravity, or the force of gravity pushing down, and then on the other side I have the pressure of the atmosphere. And I just want to know the pressure of my gas inside that tube, so I'm going to try and make my tube big enough so this pressure of my, I should say the pressure of gravity, and there's two G's, looks the same. I'm going to call this pressure of gravity as the height of the water. I want the height of my water to become 0. At that point, when they are equal, the pressure of my gas inside my tube will equal the pressure of my atmosphere, which you could look up on, weather.com or something like that. It may not be perfect, but we get a general idea of the pressure. Okay, so that's the thing of the lab. So once we apply our gas inside here, then we go back to our next step of our lab, which is to reweigh it again. Pull the little tube off this thing and reweigh it again. And you're going to get at that point, the second weighing will tell you the change in the mass. Okay. Now, again, let's go back to our calculation, which is going to be a molar mass calculation. Okay. Now, molar mass is grams per mole. You will have the mass of the liquid that you just dispensed. Okay, that's done. Easy to do. But how do I get the moles of particles inside there? We're going to gather that from Pivner. PV equals nRT. And I want this value right here. So let's solve it. PV over RT equals N. All right. Now, okay, let's start filling what we know. Okay, well, let's say that this thing is, you measure a couple things in the instructions. You'll say to measure the temperature, so there'll be a little thermometer in here. Usually the water is the same temperature as the air, so you will be able to read the thermometer. Let's say it's 25 degrees Celsius or 298 Kelvin. All right, R, if we're doing atmospheres, is 0.0821. Volume will be in liters. The tubes we have literally have a little measuring right on them in liters. Better yet, in this picture right here. Okay, so you should be able to read the liters right off of this guy and put it on there, the volume of the gas. So that point, that would be just simply read off the side. And then we have the pressure. Now, as I mentioned earlier, okay, the pressure of the gas, because of how we did it, the pressure of my gas equals the pressure of my atmosphere. Okay, now here's a little bit more information about that. Let's draw a picture of this. Okay, just a big picture, just literally the end of that gas collection tube. So here's the water, and here is the gases that are above it that are up here. And these particles are flying around, hitting walls, bouncing, and another particle flying around, hitting wall, bouncing, and there's enough collisions with all the particles in here literally to push the water down. Okay, so with that being said, what's it look like? Well, I'm going to call X the gas that we put in there. So there would be X, there would be X, there would be X, 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 X. Okay, lots of X particles, and they're all flying around. but we actually have one more particle. I'm going to call it circle, and this is water. Because this is water, water always vaporizes into the solution. Not a lot, but a little. End up getting some water molecules floating around here, and they also contribute to all the collisions, and they contribute to some of the pressure. Okay, so we have this thing called Dalton's law of what we call partial pressures. And he says that the total pressure inside this thing is equal to the partial pressure of the unknown gas plus the partial pressure of the other gases. So in this case, water and the unknown gas. All right, so at this point, how do we know? Well, it turns out that water's vapor pressure is very much linked to that of the temperature. And at 25 degrees Celsius, so at 25 degrees Celsius, which this thing is at, it is 25.6 millimeters of Hg. Okay. Now, at some point, you might say, okay, well, all right, well, what does that mean? That means, in this case, if the total pressure, now this is in atmospheres, or millimeters of mercury, so I would go get into atmosphere, because that's what I'm usually using, get rid of millimeters of Hg, and go to ATMs. 1 ATM is 768 millimeters of mercury, and then this pressure goes right here. Okay, that is the pressure of the water. And then this is the pressure of the gas, and that is what I want. Okay? This pressure here is the pressure of the atmosphere. So you put in whatever you found for your atmosphere, and then you simply subtract off the pressure of my water vapor, revealing simply the pressure of just my gas. And it's not that much. It's a small amount. In fact, in the end, we might not even realize it, but we would call this total pressure wet, meaning we're including the water. This pressure right here of just the gas we call pressure dry. Just to give you a heads up on that. So at that point, I would take this pressure and I would sub it into here, and I now have all my pieces to get my moles. In which case I plug into my molar mass formula and I get my molar mass. Keep in mind, the smallest molar mass you could ever get would be 1. 1 would be 1 gram per mole, or 1 AMU, which is a hydrogen. Just a plain old hydrogen would be 1 AMU. Cannot get a number less than 1. So we're looking to get a number here to where we could match it up to all of our original items and see which one it might be. Okay, and other than that, very straightforward, simple example of gas collection. Thank you very much.